We often picture the electron as a tiny, perfectly solid sphere of matter, but that image is false. We assume mass is an intrinsic physical ingredient of the universe, stuff you can touch, things you can weigh, and physical objects you can measure. The elastic Plenum model proposes a different reality. Mass is a macroscopic illusion, a byproduct of extreme mechanical tension acting on a quantum scale. If mass is not made of solid matter, then the building blocks of our universe are not distinct objects, they are localized actions. Menelaos Georgides' elastic plenum theory defines the vacuum of space not as emptiness, but as a tense mechanical continuum. Within this dense elastic medium, what we traditionally call a particle is a localized wave event, a temporary deformation of the vacuum itself. To prove this model, physicists had to calculate exactly how mathematically stiff this vacuum is. Finding this missing variable, the universal stiffness constant, shifts the study of the subatomic realm into the domain of concrete mechanical engineering. This diagram illustrates the electron as a soliton, a wave compression traveling through a medium that becomes trapped and freezes permanently in place. The specific shape of this trapped wave is dictated by a baseline measure known as the fundamental deformation amplitude. Its exact width, defined as the spatial localization radius, aligns with the known Compton wavelength of an electron. To describe this specific three-dimensional deformation mathematically, physicists rely on the Gaussian distribution formula. The math and the geometry show that an electron does not sit inside space. It is a highly specific, measurable knot twisted directly out of space itself. In classical mechanics, whenever you strain or stretch an elastic medium, it stores elastic energy. Applying that same rule to the quantum scale means this soliton wave holds a specific amount of trapped elastic energy. Einstein's mass energy equivalence is the bridge that connects that trapped energy to physical weight. We can substitute the generic energy variable with the elastic plenum's specific formula for trapped elastic strain. This introduces a new variable, K. The mass of an electron is the physical weight of its own trapped elastic energy. In this formula, K represents the stiffness constant of the elastic plenum. It is the single critical unknown. On the other side of the equation, the empirical mass of the electron is a known measured number. The propagation speed of transverse waves in this medium is also an established value, the speed of light. With the knowns established, we can rearrange the terms across the equal sign to isolate the single unknown variable. Finally, the geometric bounds of the electron wave provide the exact limits for the integral, completing the calculation. This method uses the known mass of one particle to define the mechanical stiffness of the vacuum medium. The precise stiffness of the vacuum evaluates to approximately 3.56 times 10 to the fourth joules per meter. Joules per meter translates to newtons of force. On a macroscopic scale, this figure represents an extreme taut mechanical tension running through all of space. This number is an invariant property of the cosmos. It does not fluctuate, regardless of where you are in the universe. Discovering this constant merges the predictable laws of continuum mechanics with the observations of particle physics. Establishing this constant allows the model to be applied to the rest of the quantum realm. Physicists can now keep the vacuum stiffness constant and use it to calculate the mass of entirely different, heavier particles, like protons. By simply altering the geometric radius of the wave, entirely new particles are formed out of the exact same medium. The geometry of the spatial torsion changes from particle to particle, but the underlying tension of the vacuum remains the same. Mass is a calculable consequence of the universe's mechanical design.